John basically asked me to come up with a list of near-term synthesis solutions, and it'll be something we can put into a notional decadal plan. And this is really, the word is notional because I really want to get people talking out at the tables and come up with things to be added to this plan, change the priorities around, and also, particularly since I had to write all these view graphs before I heard any of the talks, there's much material to be added to it. I've organized this into two general areas. First, just dealing with the movement of man into space and LEO and then beyond. And then I also want to go back and talk about the core NASA mission, which is advanced exploration. And what we're going to see is a lot of the stuff that comes out of advances in that area is going to feed back in helping in the manned exploration. So what are the big drivers in terms of using large amounts of materials in space? The construction materials, radiation shielding, all this stuff is by necessity, you have to find that locally just because of the mass involved. Whether you're on the moon, on Mars, or in asteroids. If you're in space around near Earth, obviously you're not going to build much out of a vacuum, so you got to pull it from one of the nearby resources. I would have argued for the moon earlier, but after hearing that superb talk yesterday on asteroid resources, I think that's where I put my money now. The asteroids also offer some unique capabilities in terms of the materials. If you need things which are ices, or if you need reduced metals, then you're going to get your materials from the asteroids and then move them to wherever you need them, even as to other asteroids or out to Mars. Now, by the end of the next decade, the tourist activity in suborbital flights is going to be a well-established operating industry. And we'll be starting to get into tourist and orbit, probably starting with things like, Bigelow structure stations and stuff like that, eventually evolving up to something nicer like what you're spending the evening with at Hilton or so. But wherever we build it, whether it's in LEO or GEO or on the moon, they're going to have some common characteristics. The market is going to be demanding that everything be well engineered for safety, for comfort, and also to give some maximum return for the investors. And it's also going to require, we don't know where that is going to end up with the best rewards, because that depends on the taste of the tourist. And we don't know whether they're going to like good views or a little bit of gravity, zero G sports, low gravity sports. Whatever it is, we're not going to guess that now, but the tourists will eventually tell us. But whatever it is, we're going to need a lot of support structure for that. The things that you need when you're traveling today. You're going to need food, so you'd like to have farming done in space. You got to take care of the sewage. I probably shouldn't put those two so close together when we're talking about tourists, but they are going to be related. But you're also going to need your water, your atmosphere. You're going to need medical facilities. Everything that you need when you go touring around on the Earth is going to be demanded by people who are going to go up into space. Some of them are a little bit more adventurous. I mean, people do go to Antarctica, but the big markets is in comfort. There are other people who have looked at markets for taking materials and bringing it back down to the Earth. There are some enthusiasts in here, I'm sure. I'm a bit of a pessimist on that. I think most of the materials in space are going to be used in space. The high value things that you have in the Earth market typically are not even direct products of mining. They're often byproducts of mining iron or aluminum, stuff like that. And I think that's going to be the same thing when you get these high value materials out of asteroids. You're really going there for iron. And then when you're going to start moving them down to the Earth market. But the reason they're valuable is usually because they're rare. And suddenly if you start moving material into a market with 10 times what is available before, that market value is going to crash. So when you're looking at that stuff, you have to do some really serious economic analysis about the elasticity of value in these markets. And I think there are markets there. I don't think they're going to be as big as the tourist market by any measure. And of course, the biggest market of all, if we get it going, is the solar power satellites. And I'm not going to talk about that because we're having another excellent talk by John Mankin. I think it's 2 talks from now. But when that takes off, it'll really dwarf everything else up there. And the most valuable things in space really are photons, and that you can bring back down to the Earth. Okay, the things that get the people excited, at least when I talk to them, is looking at men on bases on Mars and the moon. When we start getting to the new class of launchers, particularly the BFR class launchers, that's going to make a dramatic impact just from the lowered cost for doing that and the amount of mass that you can move, particularly to the moon. The vision, of course, of SpaceX is they can get all the way to Mars based upon that technology. That's something we can debate whether they can do that or not. And particularly like if you're going from Mars, you can really enhance that mission with nuclear thermal propulsion. And this is and also for similar missions of that sort of delta V. This is not a new idea. This is why back in the 50s, they had the NERVA rocket program. Basic characteristic is, of course, the exhaust velocities from nuclear thermal is in the 10 to 12 kilometers per second range. And that's kind of in the range for your delta Vs for Mars missions, 10 to 15 kilometers per second, depending on how you've structured the mission. And that exhaust velocity is comparable with your propulsion, so your mass ratios are reasonable. And you compare it to chemical systems, it's twice the exhaust velocity of H2O2, 3 times the exhaust velocity of methane oxygen. And so when you compare what you can do with nuclear thermal with the chemical systems, you're talking about improving your mass ratios by numbers like 3 to 8. Now, SpaceX is going to try to get there just on chemical, but that's because they don't have nuclear yet. If you come up to SpaceX and give them a nuclear stage, they'll be glad to take it. They just don't want to wait for it. And they think that they've gotten the cost enough that as hard as the problem is, they think they can actually move to Mars on it. Time will tell. If you want, the other thing I have up here is non-polar lunar bases. Clearly, the basic plan right now is to build your manned base on the poles of the moon, because there you have your solar power is available. You have the possibility of not well characterized, but real amounts of water being available, and that's going to make a big difference. So it's the only place that really makes sense for the first bases. And then you have to ask yourself, well, why would you ever leave? The views there are just about as good as any other place on the moon. And so it'll take a bit of motivation to start getting bases elsewhere on the moon. But when you get off the pole, you need something to get you through the lunar night. And that means you need either nuclear electric power or you need power beaming. For the nuclear electric, I don't think you can get that technology developed being motivated by going to lunar bases. If you're going to get that power, it's going to have to come out of other missions, and I'm going to talk about those in a later view graph. Similar, if you're trying to do power beaming from the Earth's surface, that's things we can conceivably do. Launch optics are in the 15-meter range. The receiver array, 60 meters. Talk to John, he'll wear out your ear talking about that subject. But again, I don't think you're going to get anyone to pay for that from NASA based upon trying to get a base on the moon at someplace other than the poles. You have to develop it elsewhere. I'll get back to that. Eventually, when we're building really massive things in space, and we need a lot of lunar material, that may be the thing that motivates you to go to non-polar locations. Okay, the old classic NASA mission of getting out there and exploring new areas. In the past, we've been limited as to what you can do out there, mainly because the high launch costs, because you're using our biggest launchers, the old Titan 4s, Space Shuttle, Ariane 5s. All these are very expensive. And when you get out there, you have almost no power. You're having to live off of these radioisotope thermoelectric generators, which are just giving you a couple hundred watts. And NASA has just done a brilliant job of being able to do good science out there with those power levels. But you're really limited, and you're also running out of plutonium-238. There's just so many missions you can go because there's none of the stuff available, and all the missions are competing for that small supply. The new low-cost launchers will allow you to make more missions like the one we've been doing, but you're still having to face the 238 problem. So I think what you really need to get out in this area in a new revolutionary manner is nuclear power, and in particular nuclear electric. You can start down at the 1 kilowatt level. First, the spacecraft designers are going to be delighted when you tell them you can give them, 3 times as much power for their spacecraft. And it gets you away from the 238 constraints. And you can probably launch some of these things at reasonable prices from things like the Falcon 9. But as you go up in power to something like 10 kilowatts, then you start getting some serious effects. Now you start getting into the propulsion business. You have plenty of power for your spacecraft, but now you can do an ion propulsion. The Deep Space One mission used about 2.5 kilowatt ion propulsion. The Dawn is about 10 kilowatts. So we know how to do that. We've shown in actual running missions, propulsion systems and operating the 10 kilowatt. You can use that to either get larger mass fractions out to your targets or get out there with probably not enough to get out there much faster now. But the weight of that is you're probably getting now into the low-cost heavy launchers like the Falcon Heavy class. Where you really want to go eventually is up into the 30 to 100 kilowatt range. There you get real large capacities, particularly in your propulsion system. Now we have propulsion systems which are looking in that range. The Hall thrusters have been demonstrated on the ground at least, and Vasimir gets into that range also. And so we're just starting the ground thing. Eventually you have to demonstrate the space operability of those systems, but I think we'll be able to do that by the time we get to the launch vehicles we need for these much larger things, which is getting up into the BFR New Armstrong class of launchers. Interstellar Science, I just looked up some requirements to see how you can get telescopes doing things that the current telescopes cannot do. If you want to do planetary detection and discriminate from the light of the star, you probably want things up in the 10-meter full aperture scale. If you want to look really deep, you can maybe push that to 100-meter apertures. To be able to distinguish a moon from the planet that's circulating another star system, you need to get to interferometry, and you're looking at 1 to 10 kilometer baselines to be able to get that sort of resolution. You will fill these apertures maybe with these 10-meter telescopes to get the signal that you would like. Planetary imaging, the final thing everybody wants to get to, is incredibly hard. You're looking at 1,000 kilometers and longer baselines in sparse apertures. And then if you want to launch stuff with power beaming, then you need a full aperture. And you're getting down into the kilometer and above class. In fact, I think the baseline for Starshot is like 3 kilometers. And for those, you're probably talking about launching the beam from the Earth. And so the only thing that really gets into that, and I'll talk about in the technology options. For the big apertures in space, you're not going to do that by extending the James Webb spacecraft. That's kind of broken the bank, getting only up to a couple of meters. You need some very, very new technology, thin film technologies. There are 2 options there. One is the transmissive Fresnel lens. That's kind of a different optic than most people are used to working with. But out at the Livermore Labs, we built a 5-meter demonstration of that out of a thin glass, and you can go up to much greater sizes. These are very slow lenses. F numbers are like 100. But in the floppy dimension of your optic, your tolerances go like the F number squared. So you can actually have tolerances of millimeters up to a centimeter in that, which is a lot easier to do. Transverse dimensions, of course, you built that into the glass structure, and that still has to be Lambda over 10. But with that sort of high F number and very large lenses, you're talking about a kilometer or more between your primary lens and the rest of your optical train. So it's a different type of telescope. There are ideas for reflective foils. Now you can do a very fast, more conventional telescope, but now you have to control the position of these foils to the traditional 1/10 of a wave. People have talked about ideas how to do that. Maybe it'll work in the long run. I think that's a real technical challenge to come up with that. And then, of course, down on the ground, that's where you want to go to phased array systems. There's no other way of really, you can't put these thin optics down in a gravity field with the wind blowing. And if I had a picture of our Livermore things, you can't even see the lens because it has so much support structure to protect it against the wind and to hold it up. I'm not going to talk about the breakthrough Starshot because we had a superb talk on that yesterday. I will maybe get to some other offshoots of that in the next few graphs. Mag sails, I've heard this idea tossed around. It has not been demonstrated. I haven't read the papers to really give you a lot of confidence in it. But if it does work, it'll be a really breakthrough innovation. It allows you potentially to slow down when you get to the other star if there's enough solar wind. And it's a way of generating power as you're passing through a solar wind, even within the solar system for powering your spacecraft. This is just an idea on the break. I didn't have a chance to talk with the guys from that program, so this is just all my wild guesses, and I apologize if they're too far off. But it's the idea is that the big cost drivers in that mission, of course, is going to be the lasers and the optics. The spacecraft is 1 gram spacecraft. It's clearly we can build that on the ground and in the near future, and the foils are also quite small. But if you can have precursor missions that you can then use to motivate the long-term interstellar mission, and also get into demonstrating these systems to learn about integration and operation demonstrations, this is going to be a tremendous benefit to that program. And of course, for missions within the solar system, the velocities are dramatically lower. So your laser costs and optics go down dramatically. So I just took a case here of a 1 gram payload, the old 4 meters square sail, ground laser, I said about 2 minutes. I'd launched the things from up in geo, and I'm not going to walk you through this chart, it's just to look at later. But you want velocities on the order of 100 meters per second, 100 kilometers per second to 1,000 kilometers per second. And then you can get out to the Oort cloud in times, starting maybe 2 years, get it down to 2 months. There's a lot of exciting things that you can do with this and motivate and learn about how to do this sort of technology. And at the beginning, you're really only talking about laser powers in the hundreds of kilowatts and optics that you can build today. And this can be the real way of getting in to power beaming in a serious way. Once you have power beaming demonstrated, then you can move it to other missions, like providing power for your lunar bases from the Earth. I think this is the path to get into that sort of technology. Should say a few words for the long term, beyond the next decade, but there's still a lot of dreams that we've talked about, and we still want to at least understand these. Maglev, we had just a very good talk I think it was the first day. We're going on the moon. That's clearly a winner. I was a skeptic at first, and after that talk, I can even envision the thing eventually getting off of the Earth. But I think that's a ways down the geoengineering of Earth, Mars, even Venus. I won't try to explain Venus to you unless we're sitting at a bar, but it could be done. Then there's some of the old ideas, Bob Ford's idea, and we had a talk from Tethers Unlimited. That's where the name comes from, is a technique for getting material off of the moon, and then maybe space elevators for Mars. These are still long-term dreams. But I'm hoping that we'll get conversations and the tables out there and try to figure out how do we really pull this together and put together a list of things that can be done and the crosstalk between these various ideas to make those things happen sooner rather than later. Okay.